Our universe is built on secrets we cannot see. Every moment, invisible particles and hidden forces shape the cosmos in ways that defy our senses. We are about to journey through 30 mind-bending theories that attempt to map this unseen reality. By the end, you will understand the leading candidates for the universe's missing ingredients and the revolutionary experiments hunting for them. We will ask what dark matter truly is and if particles can exist in more than 3 dimensions. What single hidden particle do you think could change everything we know? The universe might be built on a symmetry so profound it doubles the number of particles in existence. This is the promise of supersymmetry, a beautiful and elegant idea that suggests every particle we know has a hidden, super-heavy twin. Think of it as a cosmic mirror world, a shadow realm of particles just beyond our current reach. For every familiar electron, there could be a theoretical selectron. For every quark, a squark. This doubling of the cosmic cast isn't just for show. It tackles one of physics' most nagging issues, the hierarchy problem. This is the puzzle of why gravity is so unimaginably weaker than the other fundamental forces. If you think about the force holding a magnet to your fridge effortlessly fighting the gravitational pull of the entire Earth, you get a sense of this bizarre imbalance. Supersymmetry offers a neat solution. The existence of these superpartners would perfectly cancel out certain quantum effects, explaining why the gap between gravity and other forces isn't infinitely large. But the implications go even deeper. The lightest of these supersymmetric particles is a prime candidate for the universe's greatest mystery, dark matter. This stable, heavy particle would barely interact with normal matter, flowing through you and everything around you like a ghost, yet its collective gravity would be enough to sculpt galaxies. The hunt for these shadow particles is on at the world's most powerful colliders. Finding just one would be a discovery that reshapes our understanding of reality itself. Yet the mirrors remain stubbornly empty. The Large Hadron Collider, our most powerful window into this hidden realm, has been smashing protons together at incredible energies, hoping to create even a single fleeting sparticle. So far, it has found nothing. This silence is deeply puzzling. If supersymmetry is the elegant answer we suspect, why are its signature particles nowhere to be found? The simplest versions of the theory predicted we should have seen them by now. Their absence forces physicists to consider more complex and exotic possibilities. Perhaps the superpartners are far heavier than we initially hoped, existing at energy scales just beyond our current reach. Maybe they decay into normal matter in ways that are incredibly difficult to detect, leaving no clear trail in our sensors. Or, in a more radical twist, perhaps the symmetry is broken in a way that makes these particles almost impossible to produce in our colliders. Every year that passes without a discovery adds more weight to this mystery. It pushes the entire field of particle physics to a crossroads. Are we on the verge of a monumental breakthrough, requiring just a more powerful machine to finally see the shadow universe? Or is nature trying to tell us that the truth is even stranger, that the beautiful symmetry we imagined is not how the cosmos is built at all? The hunt is far from over. It is a high-stakes game of cosmic hide and seek, and the next round of experiments could change everything. This search for supersymmetric particles has led us to one of the most ghostly candidates of all. While supersymmetry proposes heavy twins, another theory suggests the answer is a particle of almost no mass. This is the axion. Born from a completely different cosmic puzzle, the axion was imagined to fix a flaw in the theory of the strong nuclear force. This force glues quarks together to form protons and neutrons, and its equations contain a term that should allow for a bizarre phenomenon. It would let a neutron, under extreme electric fields, spin in a way that generates its own tiny electric field, a property we have never observed. To explain why this does not happen, physicists proposed a new field pervading all of space, and the action is the ripple in that field. It is a whisper of a particle, billions of times lighter than an electron, and it barely interacts with anything. This ghost-like nature is precisely what makes it a perfect candidate for dark matter. Imagine a universe filled with an unimaginable number of these particles, each one so light and feeble that it passes through planets and people without a trace. Yet collectively, their sheer numbers would create the gravitational scaffolding that holds galaxies together. They would not clump in the way normal matter does, instead forming a vast, diffuse, and invisible cloud that guides the motion of stars. The search for axions is a hunt for the faintest of signals. Experiments use incredibly powerful magnets to try and convert these hidden particles into detectable photons, listening for a quiet tick in an otherwise silent detector. Finding the action would be a double victory, solving two profound mysteries at once. It would explain the strange silence of the neutron and finally give a face to the dark matter that shapes our cosmos. But what if the answer is not a new particle at all, but a hidden side to one we already know? We have met three types of neutrinos, the ghostly particles that stream from the sun and supernova, barely interacting with anything. Yet their behavior holds a strange clue. Neutrinos have been caught in the act of shape-shifting, oscillating between their three known types as they travel through space. This bizarre transformation suggests they have mass, a small but profound deviation from the standard model. To explain the full depth of this oscillation mystery, some physicists propose a fourth neutrino, one so aloof it makes its relatives seem sociable. This is the sterile neutrino. It would not interact through any of the known fundamental forces, not even the weak force that allows its three cousins to occasionally bump into matter. It is the ultimate cosmic ghost, a particle that could pass through a light year of lead without a single encounter. Its existence would perfectly explain certain quirks in the oscillation data, a hidden partner influencing the dance from the shadows. But its potential role is even grander. A sterile neutrino with a specific mass could itself be the dark matter that binds galaxies. Billions of these particles, born in the hot dawn of the universe, would have cooled and slowed, their collective gravity forming the invisible skeleton of the cosmos we see today. And the implications stretch even further to the very origin of everything. In the first moments of the universe, the decay of heavy sterile neutrinos could have triggered a slight preference for matter over antimatter. This tiny bias, amplified over time, could explain why we live in a universe of planets and stars, rather than one that annihilated itself in a blaze of pure light. The sterile neutrino is a single, elegant key that could unlock three of the universe's most profound secrets. While sterile neutrinos are ghosts, another idea points to something far more substantial. The WIMP miracle suggests dark matter is made of particles with considerable weight, yet they interact with normal matter only through the weakest force in nature. WIMP stands for weakly interacting massive particle, and its appeal lies in a stunning cosmic coincidence. In the universe's fiery first moments, all particles were constantly colliding and transforming in a dense, hot soup. As the cosmos expanded and cooled, most particle species annihilated with their antimatter partners, leaving behind the familiar matter we see today. Calculations show that if a stable, heavy particle existed that interacted only via the weak nuclear force, its annihilation rate would have naturally frozen out at just the right moment. The leftover abundance of these particles would be precisely the amount needed to account for all the dark matter we observe in the universe. This perfect alignment between early universe thermodynamics and present-day observations is the miracle. It feels too good to be a mere accident, as if the math itself is pointing directly at the answer. the hunt for these particles is a global endeavor. Deep underground, in mines shielded from cosmic rays, scientists have built ultra-sensitive detectors. They wait for the incredibly rare moment when a WIMP, after flowing effortlessly through the Earth, might nudge the nucleus of an atom, creating a tiny, measurable signal. Other experiments search for indirect evidence, scanning the skies for the faint glow of gamma rays that could be produced when two WIMP meet and annihilate in the dark heart of our galaxy. For decades, this has been the leading, most compelling hypothesis, yet, like the search for supersymmetry, the detectors have remained silent. This profound quiet is forcing us to ask a difficult question. Is the WIMP miracle a true glimpse into the hidden architecture of the cosmos, or is it a beautiful story that nature simply chose not to follow? Our struggle to find dark matter particles in 3 dimensions might stem from a fundamental oversight. What if these particles are not missing, but simply exist in directions we cannot point to? This is the radical premise of Kaluza Klein theory, a century-old idea that dared to add a 5th dimension to our universe. Its goal was a monumental unification to weave Einstein's gravity and Maxwell's electromagnetism into a single, elegant fabric of reality. In this 5-dimensional world, the forces we perceive as separate are just different facets of a single, deeper interaction. But a profound consequence emerges for particles living in this higher dimensional space. From our limited, 3-dimensional perspective, a single particle moving in a compact, curled-up 5th dimension would not appear as one entity. Instead, we would detect it as an infinite series or a tower of particles with ever-increasing masses. Imagine a single, pure musical note played on a violin string. The string can also vibrate at higher harmonics, producing a series of overtones from that one fundamental string. In a similar way, a single particle vibrating in a tiny, looped dimension would manifest to us as a whole family of particles, each with a mass proportional to the energy of its vibration. The lightest of these Kaluza Klein particles could be stable, electrically neutral, and only interact weakly with ordinary matter. It is a perfect candidate for the dark matter that has eluded every direct search. This idea forges a stunning link between the largest and smallest scales of existence. The size and shape of the hidden dimension, a property of the cosmos itself, directly determines the masses and properties of the fundamental particles we hope to detect. The search for dark matter becomes a probe of the universe's very geometry, a hunt for the hidden folds in the fabric of space. While we search for particles in hidden dimensions, another theory suggests we have been looking for the wrong kind of force entirely. Technicolor offers a completely different path to explain the origin of mass, one that does not rely on the Higgs field. In our current understanding, the Higgs boson is what gives other particles their mass, like a cosmic molasses that slows them down and gives them substance. But Technicolor proposes something far more dynamic. It imagines a new, incredibly powerful force of nature, a super strong version of the force that binds quarks together. Just as the strong force glues quarks into protons and neutrons, this techniforce would act on a new set of fundamental building blocks called techniquarks. These techniquarks would be bound together by the techniforce, not into protons, but into a whole zoo of composite particles we call technipeons, technirhoes, and more. It is this bubbling, energetic soup of techniparticles and their powerful interactions that would generate mass for all the other particles without needing a fundamental Higgs boson at all. The mass we feel and measure would be an emergent property, a side effect of this hidden, intense force operating behind the scenes. For decades, Technicolor was a leading contender, a beautiful and self-contained alternative to the Higgs mechanism. It predicted that when we built powerful enough colliders, we would not find a single, lonely Higgs particle. Instead, we would discover an entire spectrum of new, heavy techniparticles, each one a testament to this powerful new force. The discovery of the Higgs boson at the Large Hadron Collider was a major blow to the simplest versions of this idea. We found a single particle where Technicolor predicted a crowd. Yet the theory is far from dead. Physicists have developed more complex and subtle versions, where the Higgs boson itself is not fundamental, but is instead the first glimpse of this larger techni-particle zoo, a composite object made of even smaller things. The hunt is now for deviations from the expected behavior of the Higgs, tiny anomalies that could betray its true composite nature. This transforms the question from what gives particles mass to a far deeper mystery. Is the Higgs the final answer, or is it merely the doorway to a world of even more fundamental forces and particles, a world painted in Technicolor? Our story of hidden particles takes a sharp turn into the familiar world of magnets. Every magnet you have ever held, from a simple refrigerator decoration to a compass needle, has two inseparable poles, a north and a south. Break it in half, and you don't isolate the poles. You simply create two new, smaller magnets, each with its own north and south. This is a fundamental rule of our electromagnetism, but what if this rule is not absolute? Grand unified theories, ambitious frameworks that attempt to merge the electromagnetic, weak and strong nuclear forces into one master force, make a stunning prediction. In the unimaginable heat of the very early universe, this single force should have created particles that are magnetic monopoles. A magnetic monopole is exactly what it sounds like, a particle that is a pure north magnetic pole or a pure south magnetic pole existing completely on its own. Finding one would be as revolutionary as discovering an electron that carried only a positive charge. It would shatter a cornerstone of classical physics and provide direct, tangible evidence for the grand unification of forces. These particles would not be subtle or ghost-like. A single magnetic monopole would be astoundingly heavy, perhaps as massive as a bacterium, which is enormous in the particle world, and it would carry a magnetic charge so powerful it could be detected with a simple loop of wire. So why have we never found one? The dilemma is profound. Our best theories insist they must have been created in vast numbers during the universe's first moments, yet our universe appears completely devoid of them. One compelling solution is cosmic inflation. This theory proposes a fleeting epoch where the universe expanded faster than the speed of light, stretching the fabric of space itself so tremendously that it diluted the density of these primordial monopoles to almost nothing. They would be cosmic relics, so incredibly rare that finding one would be like discovering a single, specific grain of sand on all the beaches of Earth. The implications of such a discovery would ripple across physics. The existence of monopoles would elegantly explain a mystery we take for granted, why electric charge comes in discrete, quantized units. The reason an electron's charge is exactly equal and opposite to a proton's charge could be a direct consequence of the hidden presence of these magnetic particles. The hunt continues in ancient mica crystals deep underground, in cosmic ray detectors, and even in moon rocks, all searching for the distinctive scar a heavy, charged monopole would leave behind. To find one would be to hold a piece of the universe in its most perfect, unified state. The elegant simplicity of our particle zoo might be an illusion. What if the quarks and electrons we consider fundamental are not the final layer of reality, but are themselves made of something even smaller? This is the radical proposition of Preon theory. It suggests that the entire menagerie of the Standard Model, all the quarks and leptons with their different masses and charges, are just different combinations of a handful of truly elementary building blocks. Imagine our known particles as molecules and preons as the atoms from which they are built. The goal is breathtakingly ambitious: to replace the dozens of fundamental particles with just a few preons and the rules that bind them together. This could finally explain why matter comes in three seemingly duplicate generations. The electron, the muon, and the tau lepton would not be unrelated particles, but simply different vibrational states or arrangements of the same few preonic ingredients. It would demystify the precise, quantized values of electric charge we observe, revealing them as simple sums of the charges carried by their constituent preons. The theory promises a universe of profound underlying order where the apparent complexity is merely a consequence of a much simpler, hidden code, yet this beautiful idea collides with a formidable wall, the very same experiments that probe the quarks themselves. When we smash particles together at high energies, we are essentially testing their size and internal structure. So far, our most powerful colliders have seen no sign whatsoever that electrons or quarks have any internal parts. They behave as perfect, point-like dots, right down to the tiniest scales we can measure. For preons to exist, they would have to be bound together by a force of unimaginable strength, a force so powerful it confines them into such a tiny, point-like volume that our current technology cannot peer inside. This is the theory's great challenge, to explain why we see no evidence of this internal structure despite our best efforts. The silence of our detectors leaves preon theory in a difficult place, a beautiful map to a hidden world that remains, for now, stubbornly out of view. Gravity stands apart from every other force we know, while electromagnetism and the nuclear forces are all carried by specific particles. Gravity remains an outlier, described by Einstein as the curvature of spacetime itself. To unite it with the quantum world, physicists propose a hypothetical messenger particle, the graviton. This would be the quantum of gravity, a tiny packet of energy that transmits the gravitational force, just as the photon carries the electromagnetic force. But this particle is unlike any other. To replicate the unique, always attractive nature of gravity, the graviton must be a spin 2 particle. Think of spin not as literal rotation, but as an intrinsic angular momentum that defines how a particle behaves. A spin 2 particle would be far more complex than the spin 1 photon, and its properties would perfectly explain why gravity is so weak and universally attractive, warping both space and time. The challenge of detecting such a particle is almost beyond imagination. Gravity is astronomically weaker than the other forces, meaning a single graviton's interaction with matter would be incredibly feeble. To have any hope of seeing one, we would need a detector of unimaginable sensitivity, perhaps one the mass of Jupiter, placed in close orbit around a neutron star. Or we would have to observe the universe's most violent events, like the merging of 2 black holes, and look for a specific whisper in the gravitational waves, a signature that betrays the presence of individual quanta. Finding the graviton would be the final, crowning achievement of modern physics. It would prove that all of nature's forces, from the atomic to the cosmic, truly speak the same quantum language, completing a picture of reality we have been piecing together for over a century. Our definition of matter itself might be fundamentally wrong. We think of the universe as built from distinct particles, tiny specks with specific masses and properties. But what if there exists a form of matter that is nothing like that? This is the strange and unsettling proposal of unparticle physics. Imagine a substance that does not consist of individual particles, but behaves as a continuous, ethereal stuff. It would be scale invariant, meaning it looks the same no matter how closely you zoom in. A cloud in the sky is a rough analogy. From a distance, it appears as a soft, continuous shape. If you could fly into it, it would still look and feel like a continuous mist, with no fundamental building blocks revealing themselves. Unparticles are theorized to be just that, a hidden sector of reality that isn't granular, but smooth. This isn't just a philosophical curiosity, it would have bizarre, tangible consequences. In a particle collider, when two protons smash together, energy and momentum must always be conserved. We can account for the known particles that fly out, but sometimes there is a mysterious missing energy, a deficit that cannot be explained by any known particle. Unparticles could be the culprit. This continuous stuff would not register in our detectors like a distinct particle would. It would simply carry energy away silently, leaving behind an inexplicable gap in our accounting. The very way this missing energy is distributed would be a fingerprint of this scale-invariant behavior, completely unlike the signature of any conventional particle. Finding such evidence would force us to rewrite the textbooks. It challenges our most basic assumption that everything is ultimately made of things. Perhaps the cosmos is not just a collection of discrete Lego blocks, but also contains a kind of fundamental, intangible paint, a substance that flows through the cracks of our particle-based reality. This idea of a hidden reality takes its most literal form with mirror matter. Picture a universe identical to our own in every detail, a perfect reflection governed by the same laws of physics, yet completely invisible and intangible to us. In this mirror world, there could be mirror stars, mirror planets, and even mirror life, all made from mirror atoms and mirror particles. The only thread connecting our two realities is the force of gravity. This isn't just science fiction, it is a serious theoretical proposal to explain the very substance of dark matter. The mirror particles would feel their own mirror versions of the electromagnetic and nuclear forces, but they would be completely blind to our light, our atoms, and our forces. They would flow through our world as if it were empty space, yet their collective gravitational pull would be the very thing that sculpts the rotation of galaxies and bends the light from distant stars. The elegance of this solution is breathtaking. Dark matter is no longer a mysterious, unknown particle, but simply the ordinary matter of a parallel cosmos existing alongside our own. It answers the why, explaining why dark matter seems to be so abundant and yet so aloof, but it also raises a question that echoes to the core of existence. If such a mirror universe is real, what does that say about our own place in the cosmos? Are we just one version of reality with a silent twin forever orbiting us in the dark? The search for evidence is subtle. Physicists look for tiny, anomalous energy losses in delicate experiments, a sign that an ordinary particle might have briefly oscillated into its mirror twin and back, stealing away a minuscule amount of momentum into the unseen world. Finding such a signal would do more than identify dark matter. It would forever shatter our illusion of being alone in the universe, revealing that we are part of a far grander and deeply symmetrical cosmic structure. The speed of light is not just a limit, it is a cosmic border guard for reality itself. But what if some particles were born on the other side of this border, forever traveling faster than light? These are tachyons, the most controversial travelers in theoretical physics. Their name comes from the Greek word for swift, and their existence is a bizarre loophole in Einstein's theory of special relativity. The theory states that nothing with mass can be accelerated to the speed of light, as its mass would become infinite. Tachyons sidestep this by being hypothetical particles that never travel slower than light. They are not accelerating past the barrier, they simply exist entirely in the superluminal realm. This leads to mind-bending paradoxes. According to the math, a tachyon would have an imaginary mass, a mathematical concept involving the square root of -1. More disturbingly, in some reference frames, a tachyon could appear to be traveling backwards in time. This opens the door to the possibility of sending messages into one's own past, creating irresolvable logical contradictions like the famous grandfather paradox. Could you prevent your own birth by sending a signal back through time? Most physicists dismiss tachyons as mathematical artifacts rather than real, observable particles. The core issue is causality, the fundamental principle that cause must always precede effect. If tachyons existed and could be used to transmit information, they would shatter this principle, making the logical flow of the universe impossible. No experiment has ever found a definitive trace of a tachyon, and their theoretical framework is so fraught with problems that they remain a fascinating, but likely impossible, ghost in the equations. They serve as a powerful reminder of why the cosmic speed limit might be the one rule the universe simply cannot break. Our frantic search for dark energy might be looking for the wrong kind of signal entirely. There is a theory that proposes a particle so clever and elusive it actively hides from our detectors. This is the chameleon particle, a hypothetical answer to the mystery of dark energy. Its name is a perfect description of its nature. Just as a chameleon changes its color to blend into its surroundings, this particle changes its mass depending on the density of the environment around it. In the emptiness of interstellar space, where matter is sparse, the chameleon particle would become incredibly light and long-range. Its collective force would push space itself apart, accelerating the expansion of the universe and perfectly mimicking the effects of dark energy. But bring this particle into a laboratory on Earth, and it undergoes a radical transformation, surrounded by the dense matter of our planet, our air, and even the walls of the detector itself. The chameleon particle would become incredibly heavy and short-range. Its influence would shrink to a subatomic scale, making it virtually impossible to detect with any experiment we can currently design. It is the ultimate cosmic hide-and-seek champion, a particle that knows when we are looking for it and changes the rules of the game. This brilliant evasion mechanism is precisely why it remains a compelling, if frustrating, candidate. Experiments are now being devised to outsmart it, using ultra-high vacuum chambers and sensitive force detectors to try and catch the chameleon in its light state. Finding one would be a stunning revelation, proving that the force reshaping our entire cosmos is not a static property of space, but a dynamic, living field made of particles that are masters of disguise. The ghostly silence of our WIMP detectors points toward a different kind of darkness. What if dark matter is not completely isolated, but instead forms a shadow universe with its own rich social life? This is the compelling idea behind SIMP, or strongly interacting massive particles. Unlike the aloof WIMP that barely acknowledge each other, SIMP interact with themselves through a powerful, dark force. Picture a crowded room where WIMP are like silent individuals who never touch, simply drifting past one another. SIMP, however, are constantly colliding, shaking hands, and exchanging energy in a vibrant, hidden dance. This self-interaction solves a glaring problem in our cosmic models, supercomputer simulations of the universe that use simple, non-interacting dark matter often produce galaxies that look wrong. They predict that small satellite galaxies should swarm around large galaxies like the Milky Way in a dense, chaotic halo, but when we look at the real sky, we see far fewer of these small companions. The SIMP model offers an elegant fix. Because these particles are constantly bumping into each other, they smooth themselves out. They resist clumping too tightly in the dense centers of small galaxies, effectively erasing the excess satellite galaxies that our simulations incorrectly create. This internal pressure, born from their strong self-interactions, allows them to match the large-scale structure of the cosmos while perfectly reproducing the finer details we actually observe. The evidence for this hidden society could be written in the scars of cosmic collisions. When two giant clusters of galaxies smash together, astronomers can map the dark matter by watching how its gravity bends the light from background stars. In a few famous collisions, the dark matter appears to lag behind the normal matter, as if it experienced a kind of drag. For non-interacting WIMP, this is puzzling. But for SIMP, it makes perfect sense. Their strong interactions with each other would create a friction that slows them down during the violent encounter, exactly as we see. The hunt for these particles is not in deep underground mines, but in the subtle patterns of galaxy formation and the aftermath of the universe's most colossal traffic accidents. Finding them would reveal a dark sector buzzing with its own complex physics, a secret society whose internal rules have been quietly shaping the visible cosmos all along. At the absolute edge of what we can even define as a particle lies a concept of pure extremes. Planck particles exist at the final frontier of scale, where the very ideas of gravity and quantum mechanics collide and shatter. Their mass is not just large, it is the Planck mass, a fundamental unit of nature derived from the three most important constants in physics. This mass is about 20 micrograms, a tiny speck by human standards, but an astronomical mountain in the particle world. It is the mass of a grain of pollen, yet concentrated into a single, fundamental point. To understand the sheer density of such an object, imagine squeezing the entire mass of 100,000 bacteria into a volume a billion times smaller than a single proton. At this scale, the rules of our reality break down. The particle's gravitational pull becomes so intense that its own size collapses to the Planck length, the shortest possible distance in the universe. Here, the fabric of spacetime is no longer smooth. It is believed to be a seething, frothing quantum foam, a turbulent sea of virtual particles bubbling in and out of existence. A Planck particle would be a knot in this foam, a stable excitation at the very foundation of reality. Some theories suggest these are not just particles, but the true atoms of spacetime itself, the indivisible pixels from which the cosmos is rendered. The implications are staggering. The Big Bang might not have been a singular point, but a dense, hot gas of these primordial Planck particles, each one a universe in embryo. Yet for all their theoretical power, we can never hope to create one. The energy required to conjure a single Planck particle in a collider would be beyond comprehension, needing a machine the size of our galaxy. They remain a ghost in the equations, a profound reminder that the deepest secrets of the universe may be written in a script too heavy for us to ever read. The search for dark matter's hidden society leads us to a missing messenger. If dark particles interact with each other, they must have their own force carriers, much like photons carry light for our world. This is the promise of the dark photon, a hypothetical particle that would be the light of the dark sector. It would mediate forces between dark matter particles, allowing them to attract, repel, or bind together in complex ways, entirely invisible to our eyes and instruments. But this hidden messenger might not be completely isolated from our reality. Through a process known as kinetic mixing, the dark photon could have a faint, ghostly connection to our ordinary photons. Think of it as two separate oceans, our visible universe and the dark sector, separated by a vast, porous membrane. Kinetic mixing is like a tiny leak in that membrane, allowing a minuscule amount of influence to pass between them. An ordinary photon could occasionally oscillate into a dark photon, vanishing from our sight and carrying its energy into the hidden realm. This subtle effect could be our only window into this parallel world. The experimental hunt is a masterpiece of precision. Scientists use powerful lasers and intensely strong magnetic fields, trying to coax these dark photons out of hiding. They look for a very specific signature, a beam of light that inexplicably loses a tiny, precise amount of energy as it travels through a vacuum, as if some of its photons have simply stepped through a curtain into another dimension. Other experiments search for the reverse process, where a dark photon decays back into a familiar electron and positron pair, appearing from what seems like empty space. Beyond the lab, dark photons could solve cosmic puzzles. They have been proposed as an explanation for the mysterious muon G2 anomaly, a tiny discrepancy between theoretical predictions and measured values of a subatomic particle's magnetic properties. This tiny wobble could be the fingerprint of the dark photon's subtle push. They might also explain an excess of high-energy positrons detected streaming from space, a signal that could be the echo of dark matter annihilations channeled into our world by this very messenger. To find the dark photon would be to finally illuminate the laws of physics governing the dark universe, revealing that the emptiness of space is truly a crossroads between two worlds. This strange possibility of a particle being its own opposite is the heart of the Majorana fermion. In our everyday world, every particle has an antimatter counterpart with opposite properties. An electron has its antimatter twin, the positron. If they meet, they annihilate each other in a flash of pure energy. But what if a particle was so perfectly neutral, so fundamentally simple, that it was its own antiparticle? This is the tantalizing prediction of physicist Eder Majorana. Such a particle would be the ultimate lone wolf, a cosmic entity that answers to no opposite because it is the opposite. The most promising candidate for this strange identity is the neutrino. Neutrinos are already famously neutral and aloof, and if they are indeed their own antiparticles, it would solve a deep cosmic mystery. This property, known as Majorana mass, could explain why the universe contains so much matter and so little antimatter. In the early cosmos, heavy Majorana neutrinos could have decayed asymmetrically, favoring the production of ordinary matter over antimatter, providing the initial bias that led to our existence. The hunt for this ghostly signature is underway in monumental experiments deep underground. These detectors, like the Jurda and Legend projects, search for an ultra-rare nuclear process called neutrinoless double beta decay. In normal radioactive decay, 2 neutrons in a nucleus would turn into 2 protons, emitting 2 electrons and 2 antineutrinos. But if the neutrino is its own antiparticle, the 2 antineutrinos could effectively cancel each other out, annihilating before they ever escape the atom. Observing a decay that releases energy without any neutrinos would be the smoking gun, proving that the neutrino is a Majorana particle, yet the implications stretch far beyond the cosmos and into the heart of future technology. In the world of condensed matter physics, quasi-particles can emerge in exotic materials that behave exactly like Majorana fermions. Imagine an electron under extreme cold and within special superconducting materials being coaxed to split in 2. These 2 halves are not independent, they are entangled parts of a single Majorana state, appearing at the ends of a nanowire like a non-local object. Their unique property makes them incredibly robust to external noise. This inherent stability is the dream of quantum computing. In a conventional quantum bit, or qubit, information is fragile and easily destroyed by the slightest environmental disturbance. But a quantum bit built from a pair of separated Majorana states would encode information in a global property that is not stored in any single location. It is topologically protected, meaning you could jostle one end without corrupting the data, as the information exists in the relationship between the 2 distant points. Finding the Majorana fermion would therefore be a twofold revolution, answering one of the universe's oldest questions about the origin of matter while simultaneously unlocking a path to a technological future we can barely envision. Our hunt for dark matter has led us from individual particles to entire shadow universes, but one of the most colossal candidates is not a point-like speck at all. It is a cue ball, a stable and coherent blob of energy that could be roaming the cosmos. Born in the chaotic first moments of the universe, cue balls are theoretical objects known as non-topological solitons. Imagine them not as fundamental particles, but as giant, stable knots in the fabric of a cosmic field. Think of a bubble in a fizzy drink, a distinct region with different properties than the liquid around it. A cue ball is like a cosmic bubble, a vast conglomerate of a scalar field, which is a type of energy field that has a value at every point in space. What makes these objects so stable is that they carry a conserved charge, a kind of quantum number that cannot be destroyed. This charge is locked inside the cue ball, and it prevents the entire structure from simply dissolving away. The sheer size of these objects is staggering. A single dark matter cue ball could have the mass of an asteroid, all packed into a region the size of an atomic nucleus. This incredible density means just one cue ball passing through a planet would have profound effects. Its immense gravity would cause seismic ripples and create a unique, sharp signal in our detectors. Because it is a single, macroscopic object and not a shower of particles, its interaction would be a solitary, powerful event. Some theories even suggest that these cosmic bubbles could decay, releasing immense bursts of energy that we might detect as mysterious, high-energy cosmic rays with no apparent source. The search for cue balls is a hunt for these rare, cataclysmic encounters. Scientists monitor large volumes of material, from deep underground experiments to the vast stretches of the atmosphere, waiting for the telltale tremor or flash of light that would betray the passage of one of these primordial giants. Finding one would rewrite the story of dark matter, revealing it to be made not of invisible particles, but of ancient, frozen relics from the birth of spacetime. But what if dark matter is not just aloof, but fundamentally antisocial from the very beginning? This is the radical departure of the PHIMP, the feebly interacting massive particle. Unlike the WIMP, which was once in constant thermal contact with the cosmic soup, the PHIMP was a ghost from its birth. Its interactions are not just weak, they are so infinitesimally feeble that these particles never achieved thermal equilibrium at all. They never bounced and collided with the hot plasma of the early universe. Instead, they were slowly and quietly produced through a process called freeze-in. Picture the early cosmos as a bustling, energetic party filled with quarks, electrons, and photons constantly mingling. The WIMP were like guests who arrived early, chatted with everyone, and then eventually left the party as it cooled down. The PHIMP, however, were never truly guests. They were like shadows slowly cast on a wall by the light of the party inside, accumulating in silence from the rare, feeble decays of other particles. A single Higgs boson or a heavy neutrino might, on very rare occasions, decay and spit out a PHIMP. This process was never efficient, but over the entire lifetime of the hot young universe, these drips of production added up to fill the cosmos with a pervasive, invisible fog. This is a complete paradigm shift from the standard WIMP narrative. We are not looking for a particle that once socialized and then went quiet. We are hunting for a particle that was born in isolation and has remained that way for billions of years. This feebleness is its defining feature, making it impossible to detect through direct collisions in underground labs. It would simply pass through any detector without a whisper. So how could we ever find such a spectral entity? The search turns to the cosmos itself. Astronomers look for the faint, indirect signatures of PHIMP annihilations in the diffuse gamma-ray background that permeates space. Or more cleverly, they study the precise details of the cosmic microwave background, the afterglow of the Big Bang. The very process of PHIMP production in the early universe would have left a subtle imprint on this ancient light, a unique fingerprint in its temperature fluctuations. Finding that signature would not just identify dark matter, it would rewrite the entire story of its origin, revealing a cosmos where the dominant form of matter was never part of the heat and noise of creation, but a silent spectator that slowly condensed out of the fading light. Gravity's incredible weakness has always been a profound mystery, but the answer might lie not in the particle itself, but in where it is allowed to go. The Randall-Sundrum model offers a breathtakingly visual solution. It proposes our entire universe is a three-dimensional membrane, or brain, floating within a higher dimensional space. All the particles we know and love, the quarks, electrons, and photons, are stuck to this brain like ink on a sheet of paper, but gravity is different. The graviton, the particle that carries gravity, is not confined. It can leak out into the vast, unseen dimensions surrounding us. Imagine our universe as a busy city street. The people and cars, like normal matter particles, are stuck to the asphalt, but the sound of their engines, representing gravity, can travel freely into the surrounding neighborhoods and alleyways. The force of gravity feels weak to us not because the graviton is feeble, but because its influence is diluted, spreading out into these extra-dimensional volumes. This single, elegant idea explains the hierarchy problem in a completely new way, yet this cosmic leakage has a stunning side effect. Just as a guitar string can vibrate at a fundamental note and a series of higher harmonics, a graviton moving in a warped extra dimension would not appear to us as a single entity. From our perspective trapped on our brain, we would detect it as an infinite series of massive, resonating copies. These are the Kaluza Klein gravitons. Each one is a heavy, discrete particle, a specific harmonic of the fundamental graviton string. The lightest of these could be within the reach of our most powerful colliders. Their signature would be dramatic and unmistakable. In the debris of a proton collision, we would not see the graviton itself, as it would instantly disappear back into the bulk dimensions. Instead, we would see its ghostly handiwork. A Kaluza Klein graviton could decay back into a pair of ordinary particles, like two photons or two electrons, materializing from nothing. Our detectors would register a sharp, resonant spike in energy, a heavy particle that appears and vanishes in an instant, leaving behind a perfect, balanced pair of particles as its only calling card. Finding such a resonance would be a discovery of unparalleled importance. It would prove that gravity is weak because most of it exists in a realm we cannot see, and it would provide the first direct, experimental evidence that our universe is just one surface in a far grander, multidimensional reality. The search for a lone magnetic pole forces us to look deeper into the very heart of matter. If magnetic monopoles are the solitary north or south poles of legend, then what are they made of? This question leads to a theory that reimagines the foundations of magnetism, proposing that monopoles are not truly fundamental, but are themselves composed of smaller, more elusive entities. These are magnetic quarks, just as the protons and neutrons in every atom are built from quarks bound by the strong nuclear force. A magnetic monopole could be a composite particle built from magnetic quarks bound by a similar, hidden force. Imagine trying to isolate a single quark from inside a proton. The rules of quantum chromodynamics forbid it. The energy you use to pull them apart only creates new quark pairs, leaving you with more bound groups, never a free quark. Magnetic quarks would operate under a similar, profound confinement. You could never observe a lone magnetic quark in isolation. They would always be found in combinations that yield a net magnetic charge, bound together into the monopoles we hope to find. This adds a stunning layer of complexity to the strong force and the entire theory of quantum chromodynamics. It suggests that the force which glues ordinary quarks together might have a magnetic twin, a parallel set of rules governing these hidden magnetic building blocks. The universe would possess a perfect shadow symmetry, where for every property of our familiar quarks, there is a corresponding property for their magnetic counterparts. This idea transforms the hunt for a monopole from a simple search for a relic into a much deeper archaeological dig. Finding a magnetic monopole would not be the end of the story, but the beginning. By studying its properties, its mass, and how it interacts, we could potentially infer the existence and the rules of the magnetic quarks trapped inside. It would be like discovering a proton for the first time, a moment that immediately hints at a whole new, more fundamental world waiting beneath the surface. The solitary magnetic pole would become a window, offering our first glimpse into the complete and symmetrical architecture of all forces. We have explored dark photons and SIMP, but the dark sector could have a force even more powerful than our own. Dark glueballs arise from a shadow version of the strong nuclear force that binds our quarks. In our world, this force is carried by particles called gluons, and sometimes these gluons can stick together, forming fleeting, neutral bundles of pure force known as glueballs. Now imagine a complete dark copy of this system. A dark, strong force would have its own dark gluons, and these could bind into stable, massive objects, the dark glueballs. They would not be fundamental particles, but rather composite balls of dark energy held together by a force that never touches our reality. This makes them perfect dark matter candidates. They would be electrically neutral, stable for the age of the universe, and incredibly massive, but their most compelling feature is their natural tendency to interact with each other. The dark, strong force would create a rich spectrum of these states, a whole hidden periodic table of dark matter objects with different masses and properties. They would constantly scatter off one another, creating the exact self-interacting pressure needed to smooth out small galaxies and solve the satellite problem. The dark universe would not be a sea of isolated particles, but a dynamic realm of complex, interacting structures. We could never see these dark atoms directly, but their gravitational influence would be unmistakable. The search for them is indirect, looking for the subtle imprints their complex interactions leave on the large-scale structure of the cosmos, or for the faint ripples they might create in the gravitational wave background. Finding evidence for dark glueballs would reveal a hidden world of complexity, a mirror to the nuclear forces that built our own reality, operating in perfect, invisible synchrony. The sheer scale of these dark matter candidates is almost impossible to grasp, but one theory suggests the answer is not a particle at all, it is a hole in spacetime itself. The idea that dark matter could be made of black holes is not new, but it has experienced a dramatic revival. These would not be the stellar black holes formed from collapsing stars. They are primordial black holes, hypothetical relics born in the extreme density of the universe's first second. Imagine the cosmos as it cooled from the Big Bang, not perfectly smooth, but seething with quantum fluctuations. In the densest knots of this primordial soup, pockets of matter could have collapsed directly under their own gravity, stitching tiny black holes into the fabric of reality. They could span a breathtaking range of sizes, from the mass of a small asteroid to many times the mass of our Sun, all compressed into a point smaller than an atom. For decades, this idea was largely sidelined. The constraints seemed too severe. If such a vast population of black holes littered our galaxy, they would frequently pass in front of distant stars, causing a momentary brightening called gravitational microlensing. Extensive surveys of the Magellanic Clouds found far fewer of these events than a universe dominated by primordial black holes would allow, seemingly ruling out the possibility that they could account for all dark matter. But the story did not end there. The detection of gravitational waves from colliding black holes by LIGO opened a new chapter. Some of these merging black holes were surprisingly heavy, falling into a mass range that is difficult to explain through standard stellar evolution. Could they be primordial black holes, ancient fossils from the dawn of time, finally announcing their presence through violent collisions? This data has forced physicists to reconsider. Perhaps primordial black holes only make up a fraction of dark matter. a hidden population hiding in specific mass windows that have so far escaped our microlensing searches. Or maybe they cluster in the halos of galaxies in ways that evade easy detection. The hunt is now more nuanced, searching not for a single answer, but for a hidden demographic of these spacetime knots. Their existence would transform our understanding of the cosmos, suggesting that the invisible glue holding galaxies together is not an unknown particle, but the gravitational shadow of the universe's most perfect and ancient traps. These quarks are prisoners of a new and unbreakable law of physics. Unlike any particle we have encountered, a quark carries a charge for a force that never weakens with distance. This is a confining force, a kind of cosmic superglue that operates on a fundamental level. Imagine you produce a pair of these quarks in a powerful collider. The instant they are born and try to fly apart, something incredible happens. A string of pure energy instantly forms between them, a taut, invisible tether that pulls them back together. This is not a metaphor, it is a real, physical strand of the force field itself, and its tension is constant. Whether the quarks are a millimeter apart or a kilometer, the force pulling them back remains just as strong. This bizarre property leads to a detection signature unlike any other. In a normal collision, we see a spray of particles jetting out from the point of impact. But with quarks, the story is completely different. The pair would be yanked back toward one another, oscillating in a frantic dance as the energy string pulls them. They would not create clean jets. Instead, they would lose energy through radiation and friction with the detector, appearing as a single, heavy, charged object that seems to be moving through molasses. It would leave a track that is too long, too slow, and too ionizing to be any known particle. The quarks might eventually annihilate each other in a flash of light, or they could settle into a bizarre, bound state right there in the machine, a new form of matter that has never existed before. This behavior turns our entire approach to particle detection on its head. We are not just looking for a new particle, but for a new set of physical laws playing out in real time within our own experiments. Finding quarks would mean discovering a fundamental force that has been hiding in plain sight, one that operates with a relentless grip we have never before witnessed. Our hunt for dark matter has taken us from the ghostly to the gargantuan. While WIMP are massive, they pale in comparison to a true cosmic heavyweight, the WIMPzilla. This class of candidate carries a name that is no exaggeration, with masses that can dwarf standard WIMP by a factor of 1 trillion or more. A single WIMPzilla could carry the mass of an entire bacterium, an almost inconceivable amount of weight for a single particle. The very existence of such a behemoth forces a complete rethinking of how dark matter was born. Standard thermal production, where particles emerge from the hot cosmic soup, simply cannot create objects this heavy. Instead, WIMPzillas are likely relics from a far more violent and exotic process, born directly from the raw energy of spacetime itself. One compelling mechanism is gravitational particle creation during the universe's initial burst of inflation. In this fleeting epoch, the fabric of reality was stretching at a rate faster than light, a turbulent sea of quantum fluctuations. This immense stretching could have acted like a cosmic particle accelerator, ripping pairs of WIMPzillas directly out of the vacuum, their incredible mass crystallized from the energy of the expansion itself. These particles would not be children of the hot Big Bang, but rather fossils from the inflationary moment that preceded it. Their stability and sheer mass make them formidable dark matter candidates. Because they are so incredibly heavy, you would need far fewer of them to account for all the dark matter in the universe. A galaxy could be filled by just a handful of these particles passing through every cubic kilometer, their collective gravitational pull shaping the motion of stars. Their immense mass also makes them nearly impossible to detect through traditional means. They would barely notice the atomic nuclei in our underground detectors, delivering a push so weak it would be lost in the noise. The true hunt for WIMPzillas lies in the sky, searching for the indirect signals of their rare annihilations or for the unique distortions they would imprint on the earliest light in the cosmos. Finding evidence for them would not just identify dark matter, it would provide a direct window into the universe's very first instant, a time before particles as we know them even existed. Beyond the particles we chase lies an entire hidden world, a parallel reality operating just beside our own. This is the Hidden Valley scenario, a breathtaking vision of a dark sector so complete it mirrors the complexity of our own universe. Picture a vast, secluded valley separated from our world by an impassable mountain range. Within this valley, an entire ecosystem of particles exists, complete with their own forces, their own interactions, and their own laws of physics. They form atoms, molecules, and perhaps even complex structures, all completely invisible to us. The only connection between our world and this hidden valley is a narrow, treacherous mountain pass, a portal so constricted that only the feeblest of influences can leak through. This is the realm of the hidden valley particles. They are not just one new particle, but a whole new universe of them, living their lives in a reality we cannot touch. Their feeble connection to our world would manifest in a very specific and spectacular way inside our most powerful detectors. When we smash protons together at the Large Hadron Collider, the immense energy might occasionally be enough to create a pair of these hidden valley particles. Because they interact so weakly with our detectors, they would not leave a trail. They would be completely invisible as they fly away from the collision point. But then, after traveling a measurable distance, perhaps several meters, they would suddenly decay back into a spray of familiar particles like electrons and muons. This is the long-lived particle signature, a bizarre event that looks like a cosmic magic trick. Our detectors would see a collision, then nothing, and then a sudden burst of particles appearing out of thin air, displaced from the original impact. It is as if a ghost passed through the room before suddenly materializing in a shower of confetti. Spotting these events requires rewriting the rules of particle detection itself. Traditional triggers are designed to catch instantaneous decays. Finding these long-lived travelers means teaching our machines patience to watch and wait for the delayed fireworks. Each one of these displaced decays would be a message from the hidden valley, a brief, brilliant signal that our universe is far more vast and mysterious than we ever dreamed. A concept once thought to be relegated to the history books is making a quiet comeback. The ether was the great hope of 19th century physics, an invisible medium that filled all of space and served as the stage for light waves to travel through. The famous Michelson-Morley experiment famously failed to detect this motion through the ether, a result that paved the way for Einstein's theory of relativity and the idea that light needs no medium at all. But what if we have been thinking about the ether in the wrong way? Modern physicists are not reviving it as a substance for light to wave in. Instead, they are asking if the vacuum of space itself might be filled with a new kind of field, a cosmic ether that subtly breaks a fundamental symmetry of the universe. This symmetry is called Lorentz invariance, the principle that the laws of physics are the same for all observers, no matter their speed or direction. A modern ether field could provide a preferred frame of reference, a subtle background direction to the cosmos that would violate this perfect symmetry. The effects would be incredibly tiny, perhaps changing the speed of light for different colors by a minuscule amount, or altering how particles spin as they travel across the universe. Detecting such a violation would be like finding a secret North Star for the laws of physics themselves, this new ether would not just be a historical curiosity. It could be the very substance of dark energy, a field whose energy permeates every cubic centimeter of emptiness and pushes the universe apart. The ancient philosophers who dreamed of a cosmic plenum filling the heavens were, in a way, correct. They just lack the mathematics to describe its true, dynamic nature. The hunt is now on for the fingerprints of this new ether, searching for tiny anomalies in the light from distant gamma-ray bursts or in the precise behavior of subatomic particles in orbital experiments. Finding them would mean that the void is not empty at all, but alive with a hidden structure that has been guiding the cosmos all along. Electric charge seems to come in neat, whole number packages. Every particle we have ever found carries a charge that is a simple multiple of the electron's charge. This rule of charge quantization is a cornerstone of the Standard Model, but what if it is not the full story? Theory 28 dares to propose particles with fractional electric charge. The most famous examples of this are quarks, which carry 1/3 or 2/3 of the electron's charge. But here is the catch: quarks are perpetually confined. You can never isolate a single quark to measure its bizarre fractional charge. They are forever bound inside protons and neutrons by the unbreakable grip of the strong force. The search for fractional charge is a hunt for a free quark, or for an entirely new fundamental particle that carries a fractional charge and exists freely in nature. Finding one would shatter a fundamental principle of physics. Experiments have hunted for these fractional charges with incredible ingenuity. One of the most famous searches involved meticulously measuring the charge on tiny superconducting niobium spheres. If a particle with 1/3 the electron's charge were trapped in the sphere, it would cause the total charge to be a fraction rather than a whole number. Scientists measured millions of these spheres, cooling them to near absolute zero and using sensitive magnetic fields to detect any deviation from whole number charge. Other experiments have sifted through cosmic rays and the debris of particle collisions, searching for any track or signature that betrays a fractionally charged object. So far, the results have been a profound silence. No confirmed free quark or fractional charge particle has ever been found. This silence is itself a powerful statement about the nature of reality. It strongly supports the idea that confinement is an absolute law, that fractional charges are forever hidden from our direct observation. Yet, the implications of a discovery would be so revolutionary that the search continues. Finding a free fractional charge would mean that our understanding of electromagnetism is incomplete. It could point to new, deeper symmetries in nature or reveal that the vacuum of space itself has properties that force charge into whole numbers under normal conditions. The hunt for these fractional charges is a test of one of physics' most deeply held beliefs, a quest to see if the universe's ledger of charge is truly as neat and tidy as it appears. The universe's most energetic particles arrive without a return address. Ultra-high-energy cosmic rays strike our atmosphere with the force of a well-thrown baseball, all concentrated into a single, invisible projectile. Their origin is one of astrophysics' most enduring puzzles, but a solution might lie in the decay of a ghost from the earliest moments of time. Kryptons are messengers from the string scale, hypothetical particles predicted by some models of string theory. In the hot, dense beginning, these particles could have been forged in the same fire as everything else, but with a crucial difference: they are staggeringly long-lived, stable across billions of years due to a hidden symmetry that almost, but not quite, forbids their decay. Think of a diamond locked in a vault with a million combination locks. A krypton is like that diamond, protected by a complex set of quantum rules that make its disintegration an incredibly rare event. Yet, over the vast age of the cosmos, a tiny fraction of these ancient relics would finally succumb, decaying into a shower of familiar particles. the energy released in that single, final moment would be colossal, channeling the immense mass of the krypton directly into a burst of ultra-high-energy protons and other radiation. This would be a cosmic-scale firecracker, a single decay event so powerful it could propel a particle across the universe with the energy we detect in our atmosphere. The beauty of this theory is that it connects the impossibly small world of strings to the grandest explosions in the sky. Kryptons would be fossils, carrying within them the specific energy of the string scale, a fundamental limit of nature. Each ultra-high-energy cosmic ray could therefore be a data packet from the dawn of reality, a final message from a particle that witnessed the universe's first breath. Their detection would offer more than an answer to a cosmic mystery. It would provide our first experimental clue that the fundamental fabric of reality is woven from vibrating strings. Our final hidden particle ties together two of the most profound ideas in physics. The gravitino is the hypothetical superpartner of the graviton, emerging when we apply the principles of supersymmetry to gravity itself. This union creates a framework known as supergravity, and the gravitino is its crucial messenger. If the graviton is the quantum of gravity, a spin 2 particle, then the gravitino is its shadow, a spin 3 half superpartner. This unique spin makes it a fermion, a particle of matter, but one inextricably linked to the force of gravity. It would be the ultimate bridge between the cosmic and the quantum, between the force that shapes galaxies and the particles that constitute them. As the lightest superpartner in many supergravity models, the gravitino naturally becomes a prime candidate for dark matter. It would be stable, neutral, and only interact through gravity and perhaps the weak force, flowing through the cosmos as a ghostly, pervasive cloud. Yet this elegant solution comes with a potentially catastrophic catch, known as the gravitino problem. If the gravitino is too light, it becomes a relic that threatens to overwrite the history of our universe. In the hot, dense conditions following the Big Bang, energetic particle collisions would have produced gravitinos in enormous numbers. The problem lies in how they decay. A light gravitino would be unstable, decaying over long timescales into ordinary particles in light. These decays would inject a tremendous amount of energy into the early cosmos, fundamentally altering the nuclear processes that forged the first light elements. The predicted abundance of helium and deuterium that we observe today would be completely different, clashing violently with our precise astronomical measurements. The universe we see simply would not exist if light, unstable gravitinos were abundant. This problem forces a difficult choice upon the theory. Either the gravitino is so incredibly heavy that it was never produced in significant numbers, or it is perfectly stable and constitutes the dark matter, but only if its mass is just right, typically in the range of 100 to 1,000 times the mass of a proton. Finding the gravitino would therefore be a two-fold triumph. It would be the direct confirmation that supersymmetry is not just a property of matter, but a local symmetry of spacetime itself, validating supergravity. We would finally understand how the quantum world and gravity intertwine at the most fundamental level. Its detection, however, presents an almost insurmountable challenge. Because it interacts so feebly, a gravitino could pass through a planet made of solid lead without a whisper. Our only hope might be to observe its indirect influence on the precise spectrum of cosmic rays, or to find its signature in the delicate physics of the very early universe. The gravitino stands as a final, majestic piece of the puzzle, a particle that promises to unite the largest forces with the smallest particles, if only we can learn how to see it. Our journey through the hidden particles of the cosmos reveals a stunning truth. There is no single answer, no solitary ghost waiting in the dark. Instead, we are faced with a breathtaking spectrum of possibilities, from the ghostly whisper of an axion to the colossal weight of a WIMPzilla. from particles trapped on our brain to those roaming the wilds of extra dimensions. Each theory is a different key, forged from the fire of human curiosity, each one designed to unlock a different door in the mansion of reality. The sterile neutrino offers a single, elegant solution to multiple cosmic riddles, while the vibrant society of SIMP paints a picture of a dark sector buzzing with its own complex life. Some keys, like the gravitino, promise a grand unification of all we know, while others, like unparticles, challenge our very definition of what a thing is. This incredible diversity is not a sign of confusion, but a testament to the depth of the mystery. We are mapping the edges of the unknown, and every proposed particle, from the humble Preon to the cosmic cue ball, represents a different path forward, a different story about how the universe might truly work. The search itself is what matters, this collective effort to listen for the faintest whispers from the dark. So we turn the question to you. Which of these 30 keys do you think fits the lock? Which hidden particle, from the shadow twins of supersymmetry to the chameleon hiding in plain sight, captures your imagination? Share your thoughts in the comments below, and if you are ready for more journeys to the edge of understanding, be sure to subscribe. Our exploration of the cosmos's deepest secrets has only just begun.